last page of dynamics. Huzzah. What do they have for us now? A 60-kilogram man is standing on a scale calibrated in newtons inside an elevator. Determine the apparent weight of the man as shown by the scale as the elevator is accelerating. So, the thing to know here, it is very common and very understandable to say that scales measure weight. They kind of don't. Scales measure normal force. When you stand on a scale, the scale measures how hard am I being crushed between this person's feet and the floor. Now, 99% of the time, if you have a scale on the floor in your bathroom, your weight and the normal force are going to be exactly the same, and so the scale is going to read accurately. But we need this normal force fact because you can fool a scale by putting it in an elevator. And let's see how that can happen. For now, what I want you to take away is that scales don't measure FG, they measure F normal. How hard are they being pressed on by the person's feet? And here's what that can mean. If you're in an elevator, here's our person, and here is our scale between the person's feet and the elevator floor. What's the weight of this person, first of all? You can always find the weight of something by doing mg. What's the mass of the thing times how strong is the gravity it's sitting in? For this person, the answer is 60 kilograms times 9.81 newtons per kilogram if they're on Earth. And as soon as I get my calculator app open, 60 times 9.81, 588.6 newtons. Is the gravitational force pulling down on this guy. 588.6 newtons. And the other force acting on him would be a normal force pushing up on his feet through the scale. And if we want to put all this together, Newton's second law says F net equals ma. And the net force is made up of a normal force we don't know yet, and negative 588.6, that's gravity pulling down, equals his mass times, they say his acceleration is 1.3 meters per second squared. So we put that in there. Normal force minus 588.6 equals 60 times 13 is going to be 78. And then if we want normal force by itself, we do 588.6 plus 78. And we get 666.6 newtons. And does everything have... This has 3 sig digs, but this only has 2, so we're stuck with 2 significant digits. We should be going to... Or are we? Let me be careful about this. 60.0 times 1.3. Yeah, the 78 has 2 sig digs, which means it has 0 decimal places. So when we add this over, we should get an answer with 0 decimal places, meaning it should be 667. Oh, good for them. They actually got the precision right on this. Took me a second, but I agree, 667 newtons. This one was a combination of multiplying and adding, so we had to use both the significant digit and the decimal place rule to get it correct. So, if this guy stood on a scale just in a regular room, it would read 588.6, which is his normal weight. But in the elevator accelerating up, you've probably felt this in elevators, you feel a little heavier when the elevator's lifting off. That's this. Your normal force is higher. This is what they call your apparent weight. And you feel it, and a scale gets fooled the same way, and it feels like you're heavier when the elevator's lifting off, because the cables are having to pull not just hard enough to support your weight, but also enough to get you moving upward, and that extra pull results in some extra force on your feet. Extra apparent weight. Let's try it again. I'm keeping that 588.6 because we're going to need that again. That's the guy's weight when he's not in an elevator. If we set this up again, F net equals ma, we still have F normal and gravitational force together, making his net force. We don't know the normal force for this descending elevator. Gravity is still minus 588.6 because Earth doesn't care how you're moving. It pulls the same amount all the time. His mass is 60. And now they say we're accelerating down 2.1, so negative 2.1 for the acceleration. F normal minus 588.6 equals 126, negative 126. Negative 126 plus 588.6 gives us 462.6, or to 3 with 0 decimal places, 463 newtons. So he's 588.6 on normal ground, but with the elevator descending, he only feels like he weighs this much. And you've probably felt this too in an elevator. You feel kind of light when the elevator descends. That's because the tension in the cable is less. The elevator's letting you fall a little bit. With the floor dropping out from under you like that, your apparent weight goes down. There's less force between your feet and the floor because the floor is falling away from you. So, Newton's second law, good stuff. And what's our last thing? A 250-gram racquetball is moving toward a player at 3 meters per second. It's actually a fairly good racquetball color. And it's hit, so it changes direction, giving it a speed of 5 in the opposite direction. Calculate the magnitude of the force if it was in contact for... Okay, so the ball has an initial velocity of 3. We'll say it's going to the right. Then it gets hit and goes back the other way, so its new velocity is 5 in the opposite direction. We'll call that minus 5. These are both meters per second. And it does that in 0.6 of a second, which sounds a little long, but we'll live with it. And they want force. Well, we know we can get force from this, which would be fine as long as we had an acceleration. And we can get an acceleration because we have acceleration equals Vf minus Vi over t. Or your sheet, you may have learned it delta V over delta t, which means the same thing. How much did your speed change divided by how long did it take? That's acceleration. So the acceleration here is V final is negative 5 minus V initial is 3. Elapsed time is 0.6 of a second. Minus 5 minus another 3 is minus 8. Divided by 0.6 is minus 13.3 meters per second squared. And now that we have that, we can find the force. The force on this ball would be its mass. They gave us 250 grams, but we'd rather have kilograms, thanks. Accelerations minus 13.3 meters per second squared. And doing that, you get 3.3 newtons. Technically, it should be negative, and their answer doesn't say anything about the direction, but of course the direction would be opposite the original direction. The ball comes in like this, you swing to the left and knock it back the opposite way, so the force you exert will be opposite the way the ball was originally moving.